Good day, ladies and gentlemen. You are welcome to our lecture number 5 on CHEN723 Basic Electronics, and this lecture is our last lecture in this course, and it will be about digital electronics. So far we have been discussing on basic electronics components and their applications in amplifiers, power supply, and what have you, and almost all of them we categorize them as analog electronics because they are dealing with time varying signal. That is a signal that is continuous in nature. If you look at this waveform, wherever you touch on this curve, you can have a corresponding value. But the digital electronics, on the other hand, it doesn't have the continuous values, but it has what we call discrete values. And of course, the values are represented in a binary. And we know binary is a 2-bit system with 2 bits. The first one is 0 and the second one is 1, but there is nothing in between 1 and 0. And sometimes this 0 and 1, we call them high and low, where high is 1 and low is 0. Sometimes we call them on and off, that is 1 and 0. So these bits, they are the only possible results you can have in any digital system. It has only 2 values, either high or low, on or off, 1 or 0, but nothing in between. Now, this analog, as I've already explained, it is continuous in nature. This is the waveform of the analog. But if you look at this one, wherever you have a signal, it will have its full value, which represents 1, and where it is absent, we have 0. Full value 0. But here, if you touch here, you can have a value. If you touch here, you can have a value. Wherever you touch, you can have a value. So why do we need, and why is this digital electronics is important? These are some of the advantages. It is very much easier to design than analog, and it has higher accuracy in terms of data, and it is programmable. That is, you can program it to do whatever you want it to do using microcontrollers, and it is having noise immunity. That is, it have the power of rejecting noise, that is signals from the other sources. And of course, it has easier storage of data. All our flash, our DVD, our hard disks, they store information in digital form because it is easier. And also it is having ease of fabrication in form of integrated circuit. Whenever you want to design an integrated circuit, you either design analog or digital. But the digital has advantage of being easier in fabrication compared to the analog. There are many applications of this digital electronics. The first one, it is used in communication. Our television stations, our radio stations, our telecommunications company, satellites, all of them, they use digital signal. They are used in business transaction. Go to bank and see. We are using computers. You that can make an online transaction, you use a digital computer or your handset. It is used in traffic control, and it is also used in spacecraft guidance, that is controlling the flow of aeroplanes and other missiles in the sky. And also it is used for medical treatment. Most of our diagnosing equipment for diagnosis and of course for operations, they are what? Digital in nature. And also they are used for weather monitoring, that is weather forecast, to know whether today it will be hot or it will be cold or there is rain or anything like that. The equipment we use, they are mostly digital in nature. And in our internet browsing, of course, ultimately computers are digital in nature. And we have so many other applications in the areas of commercial, industrial, and scientific enterprises. So the next thing is we are going to be looking at what we call Boolean Algebra. And this Boolean Algebra is something that has to do with design of what we call logic gates. These logic gates, they are electronics component. Of course, most of all of them, they are made using discrete components like resistor, capacitor, transistors. But we use them for allowing signal to pass through them, whether to have high or to have low, depending on the type of the logic gate and also the nature of the input you supply to it. So this logic gate, as I said, they will accept digital input and they will give you an output. The digital input can be 1 and can be 0, that is low or high, and it can also produce a corresponding output which can be 1 or 0, as we are going to see very soon. And the inputs and the output of all the digital gates are of course only two levels, high or low, true or false, on or off, which simply means 1 or 0. And we have a table that shows the relationship between the inputs to any logic gate and the output, and this table we call it a truth table. And we have different categories of families of logic gate. One of them is what we call TTL, transistor logic. In this form, we assume 0 volt is our low and 5 volt is our high. So anything that is closer to 5 can be approximated to 5 to have our logic 1. Anything that is much closer to 0, it will be approximated to give us logic as 0. And we have different types of logic gates, as we are going to be discussing now one after the other. Let's start with the first one. We call it AND gate. AND gate. The AND gate is a gate that can have at least 2 inputs. It can have 3 and it can have more. And its nature of operation is that if it has 2 inputs, for instance, only when all of the input 1 and 2, all of them are 1 1, then the output should be 1. But whenever you have one of them is 0 or all of them are 0, then the output should be 0. So this is the symbol. This is the symbol of what AND gate. And you can see here I have pin 1 and pin 2 as my what inputs. The pin 1 I call it X, the pin 2 I call it Y, and the output is pin 3 and I call it Z. So whenever X and Y are all 1 1, then Z is going to give you 1. But wherever at least one of them is 0, the output should be automatically 0. And this is the truth table we talked about. These are our inputs and this is our output. I told you from the diagram, from the symbol, X and Y are the inputs and Z is the output. So we said whenever X and Y, all of them are 1, that is the only place we should have Z equal to 1. For instance, one of the possibilities, X can be 0 and Y can be 0. Then X can be 0, Y can be 1. X1, Y0, 1, 1, all of them. These are the only possible combinations for them. Because I have 2 inputs, 2 raised to power 2 will give you 4 combinations. So when both of them are 0, Y is 0. When X is 0, but Y is 1, still Z is 0. When X is 1 and Y is 0, the output still is equal to 0. The only condition for output to be 1 is when all the input X and Y are equal to 1. And for this reason, we call it AND gate, because X must be 1 and Y must be 1 before Z can give you 1. And also this is another diagram which is the same thing to this, but here I have 3 inputs, WXYZ, WXY, and my output is Z. And you can see from here, Z is equal to X times Y. X times Y, because it is AND. And you can see it easily. If you say 0 times 0 will give you 0. 0 times 1 still is 0. 1 times 0 is still 0. It's only when they are 1 times 1 should give me 1. So here I am having another version with 3 inputs, WXY, and my Z is the output. Since there are 3, I have 8 possible combinations. 2 raised to power 3 is 8. From 000, 001, 010 up to 111. And as I told you, when at least one of them is 0, the output should be 0. You can see all of them 0, 0 here. 2 of them 0, 0. Here 2 of them also 0, the output is 0. Here I have only 1 0, but 0 times 1 times 1 is still 0. So if you look at all the combinations from the first one up to number 7, at least one of the WX is 0 and therefore Z is 0. It is only the last one where X is 1, Y is 1 and Z is 1, then my output is what? 1. That is W, X and Y, all of them are 1. Then 1 times 1 times 1 will give me 1. So this is AND gate. All the input must be equal to 1 before the output can give you 1. But if at least one of them is 0, then automatically the output is 0. The second one is what we call OR gate. And from the name, this is a gate that when at least one of the input is 1, because if the two inputs are x and y, when x or y is 1, then the output should be 1. The only condition where the two of them will give us 0 is when x is 0 and y is 0. Look at the symbol here. You can see that it is different from the AND gate because here there is a curve, but for the AND gate is what? Straight line. So let's assume these are my input x and y, and the output is z. So this time around, instead of x times y, is x plus y. When two of them are 0, 0, it means 0 plus 0 is 0. But when x is 0, y is 1, so 0 plus 1 is 1. And of course, when x is 1 and y is 0, 0, 1 plus 0 is still 1. But here, if we say 1, 1, we don't mean 1 plus 1. In binary, you know the value is only 1. So all of them are 1, therefore the output is what? 1. So what are we saying about the OR gate? We are saying whenever at least one of the input is 1, the output should be 1. The only place where I have 0 is when x and y are all zeros. Now look at the second type. It is the same thing with this, but here we have 3 input. And for 3 input, as we have seen in the case of AND gate, we have 8 possible combinations, 2 raised to power 3. So it starts from 0, 0, 0 up to 1, 1, 1. So the only place where I should have 0 as the output is when w, x, and y are all 0, then my output should be what? 0. But when at least one of them is 1, you can see all the outputs are what? 1. The next one is NOT gate. NOT gate. This NOT gate, sometimes we call it inverter, because it will give you opposite of the input. When the input is 1, the output should be 0. And when the input is 0, the output should be 1. So that's why we call it NOT gate or inverter. It is having only one input and it has one output. And it is the device whose output is always complement, that is opposite of what? The given input. If x is 1, the output z it should be 0. Here is the table. Here is the input, here is the output. When input x is 0, the output should be y. When the input is 1, the output should be 0. That is the inverter application. Now the next one is what we call the NAND gate. This NAND is combination of 2. That is, or before that, the NAND gate and the NOR gate, we call them universal gates. The reason why they are called universal gates is that we can use them to create AND gate, to create OR gate, and to create NOT gate. So therefore, they are called universal. So let's start with the first one, which is NAND. This NAND gate is a combination of 2, AND and NOT. AND and NOT. If you can see this diagram, is the symbol of AND gate. But at the terminal output here, I put a circle. And that circle is standing for the NOT. So what are we saying? We are saying this one will be operating directly opposite to AND gate. If you can remember, in the AND gate, only when x and y are 1, we can get 1. But here, the reverse is the case. When x and y are all 1, the output should be 0. But when at least 1 0 exists, we have 1 1 1. And if you go back to AND gate, it is directly opposite. Because in the AND gate, we have seen that only when 2 inputs are 1, we can get 1. Let me go back to the AND gate. This is the AND gate. When x is 1, y is 1, we can have what? 1 as the output. But in all other conditions, we have 0 as the output. So in this case, you can see when x and y are 1, we have 0, but all other ones, they should have 1. Therefore, it is what? Negation or opposition to what? AND gate. That's the meaning of NAND, not AND. The next one, we call it NOR gate. And this NOR gate, as I told you, is one of the universal gates itself and the NAND gate. And it is combination of 2 also, not OR gates. So it is operating in opposite to the what? OR gate. If you can remember, let me go back to OR gate. We said when at least one of the two input is 1, you will automatically have 1 as the output. But when all of the input are 0, you have what? 0 as the output. But in this NAND gate, or NOR gate, sorry, when X and Y are 0, the output should be 1. But in all other cases, I will have 0. This is directly opposite of OR gate, and that is why we call it not O. And the last one, second to the last one, we call it exclusive OR gate. Exclusive OR gate. I want to take us back to the OR gate. You can see that from the OR gate, whenever at least one of the input is 1, you can have what? 1. When the two of them are 1 also, you have what? 1. But in this negation we are going to be talking about, that's exclusive OR gate. It is the one in which when either X is 1, or Y is 1, we have 1. But whenever two of them are 1 or two of them are 0, the output should be 0. Therefore, we call it exclusive OR. And for this reason, we call it non-coincidence. That is, whenever the X and Y coincides, they are either all 1s or all 0s, the output should be what? 0. And for this reason, we call it non-coincident. So the last one is exclusive NOR. And the exclusive NOR, the NOR gate is what? Negation of the OR gate. In NOR gate, we have seen that when the two of them are all 0s, when all of them are 1s, the output should be what? The 0. Let me go back to the NOR gate. This is the NOR gate. You see, when all of them are 0, I have 1. In all the other cases, I have 0. But this exclusive NOR, it is the one in which whenever either X and Y are 0, 0 or 1, 1, the output should be 1. But whenever they are different, as you can see here, we have 0, 1, here we have 1, 0, the output should be what? 0. That is whenever the inputs are equal, all of them equal to 1 or all of them equal to 0, the output should give me 1, 1. But wherever they are different, it will give me 0, 0. And that is the reason why we call it coincidence gate. Because when they come to 0, 0, I have 1. When they come to be 1, 1, I still have 1. So this is the end of this lecture. And of course, this is the end of the course. As I always tell you, I want you to watch these things several times. It will make it very easier for you to understand. And of course, I'm going to do one thing. I extract all the possible questions and I'll give them to you. You use your PowerPoint and your videos to produce the answers. And that number of questions I gave you, definitely they are the ones that I will be asking you in your CA and in your exam. So thank you very much, and I wish you successful CA test and exams. Thank you.